Okay, I'm ready to go. Can you see my screen?
Yep.
Yep.
Thank you. Yeah, so maybe that was an overkill, but there was a storm warning, so I'm not sure whether it was worth it to move the lecture online. But anyway, we did it already. So hope you guys had a good break. So I didn't feel like asking TAs to work through the break. So they started grading yesterday and they will finish by the end of the week. Um, I mean, I hope the exam wasn't that hard because really we kind of try to keep it in line with everything else with what we reviewed during the class. So, but feel free to tell me how you feel about it. But now, okay, so also another announcement. So I reopened homework 3 just because I keep getting emails asking for help, and there was a break and people didn't get enough time to essentially talk to the TAs and make sure that they have enough support. So I like it seems okay to open it until Thursday. So if you suddenly have a late penalty or you didn't finish something or you want to do more extra credit, go ahead and submit by Thursday night. Other than that, we will probably assign a new homework on Thursday, and our goal today is to kind of come back to the interrupts and exceptions and cover the xv6 system calls. And the idea here is the following, right? So just a quick reminder. So like we talked about, again, internals of the L files. We talked about how you boot into the main function. You did the homework. Now supposedly it's all clear. You know how to boot into main. And at this point, we're kind of building the operating system kernel, right? And at a high level, again, our goal is to make sure that we have user processes running. So this is user main here, whatever you want to build here. Maybe it's a shell, maybe it's some kind of Apache thing, like a web server, maybe it's something simple like WC. So you have a main, and this main interacts with the kernel through the interfaces of system calls, right? So those are the syscalls. And our goal is that we will run, obviously, all the user programs in ring 3. And remember, we're gonna quickly review what these privilege levels are, but the idea is that kernel runs in the most privileged level, ring 0, user runs in ring 3, and the only way for the user to access the kernel is to invoke a system call. Think of it as a security check. Like a real world analogy would be something PSA checkpoint at the airport, where you essentially the system call entry point will check whether the arguments are well formed, whether all the pointers point to the user level and not trying to like overwrite or read the kernel's memory, stuff like that. So we'll take a look at it. So the kernel runs here, kernel, just again, reminder, some instructions like move into control register 3, which is the page table, will be privileged, meaning that you cannot invoke them in ring 3, right? So they are only invocable in ring 0, right? And so that's why this is essentially the nature of this privilege separation. So some things which protect the integrity of the platform can be only invoked from ring 0, and user level can invoke regular CPU instructions and can invoke instructions which allow user level to enter into the kernel through the interface of the system calls. And we will see that this instruction will be an int instruction which invokes an interrupt. But other than that, user cannot it cannot change the global descriptor table, cannot change the page table, cannot trigger interrupts in an uncontrollable manner, stuff like that, right? So everyone understand this? So by the way, feel free to interrupt me anytime. So treat it as a normal lecture, and you don't have to raise your hand, just like ask a question, but I will stop for a second if there are for any questions. All good? Okay, so just a quick detour since we did it like almost 2 weeks ago. Like, remember, I talked about privilege levels, and the question again, the natural question is what these are again, and like we talked a lot about it, like in passing. So we kept mentioning this idea many times that, user cannot access the kernel memory in an uncontrollable manner, right? And on Intel CPUs, the original way to implement this idea was to introduce 4 privilege levels, and those were called rings. Ring 0 was the most privileged. Ring 1 was more privileged than ring 0, was less privileged than ring 0, but more privileged than ring 2. And finally, ring 3 was the least privileged, right? So it goes like the most privileged to the least. And the idea was that set on instructions like moves into the global descriptor table, into the CR3 can only be invoked in ring 0, and user level cannot invoke those instructions at all, right? And the question is like, how does the x86 keep this ring? So how do we keep information about which ring we're running in? And the way it's done is that the moment we switch to a specific segment, or more specifically code segment, which we grab from remember when we initialized the global descriptor table, and you did it in your homework, right? So we put some descriptors here. And this is an example of a descriptor. And essentially, the very first time we jump, like we do a long jump, remember we did it in your homeworks, it's CS and some function like, I don't know, foobar, for example. And the CS will get picked from the global descriptor table because it's essentially a pointer. This number points to the global descriptor table. And inside this global descriptor table, we'll have this entry, which consists of like 64 bits, right? And one field, which has 2 bits here, will encode the descriptor privilege levels, right? And when you configure the system, obviously, in order to stay in a most privileged level, the very first long jump, which we do, will have this privilege descriptor, this privilege level set to 0, right? Which means that when we boot, we essentially stayed in privilege level 0. And we run in privilege 0, we reach main function of the kernel, and later on we will see how the first process is initialized. But essentially, when we will exit into the user level, we will change this code segment to point to the privilege level, the descriptor which has a privilege level 3, right? And this is how we essentially exit into the user level. Do we all remember how it works? Any questions about it? So just again, reminder, remember Intel has this funky mode of execution, which is called logical address, consists of 2 parts. The offset, which we usually see in the register when we use a move instruction or something, and the segment selector, for example, code segment or a data segment or a stack segment, they point in the global descriptor table. This chooses the segment descriptor, and these things will have descriptor privilege level. So for example, or 3, right? And that's essentially how it works. We like the operating system, which initialized this privilege level, sets a number there. And again, just starting from boot, when we booted, originally we ran in real mode, no privilege levels, no global descriptor table. The first time we do a long jump in x86, starting to the function entry start 32, we use entry number 1 in a global descriptor table, and this entry number 1 has this descriptor privilege level configured to be set to 0. And the way we did it, we used those macros in x86, which essentially said, okay, by the way, both the code segment and the data segment in x86, it's inside the macro itself, will have the privilege level 0. And essentially, when we chose this entry with descriptor privilege 0, we are running in a ring 0, right? Or if you use correct terminology, it will be called current privilege level is equal to 0, and we are continuing in a kernel. We keep booting like that, right? And then the very first time we return to user, and I will explain how it works today. We'll use an iret instruction, this IRET instruction, which will use the code segment number 4. So essentially 0, 1, 2, 3, 4. This entry in a global descriptor table. This entry will be configured with descriptor privilege 3, which means that the next instruction after the IRET, essentially pointed by this instruction pointer, this EAP, whatever it is, some move instruction or something, will be executed with code privilege level equals to 3. And we're running in ring 3. So if you try to do a move into the CR3 register some value, this instruction will cause an exception. It will be a protection violation exception because we say, look, in ring 3, the changes to CR3 to the control registers are not allowed. Does it make sense? Okay, so now let's take a look. Last time we talked about the interrupts and I explained the idea, how it works, how the interrupt transition works when you don't change the privilege level. But now let's discuss how it works when we essentially, how the interrupt transition works when we switch from ring 3 into the kernel. A short detour here is that I wanted to explain again. So how is this global descriptor table is initialized in x86? Remember, we entered the main function. This kinit1 initializes the physical memory allocator, so that creates a linked list of available pages. It doesn't take the entire memory. It only goes up to the first 4 megabytes, and it goes from the end of the kernel to the 4 megabytes. That's because that's the only memory which is currently mapped. We initialize local interrupt controllers. We're not going to talk about them right now, but this function, which initializes the global descriptor table, is the one which essentially configures it in x86. So the way it's done is when you enter this function, so again, here I have a call stack of a function, so it's called seginit is called directory from main. Since x86 has abstraction of multiple CPUs, it says, okay, I'm running on a CPU 0, for example, now, or maybe 1, or maybe 2, but this CPU ID returns the current ID of the physical ID of the current CPU. It returns the data structure of like struct CPU, and this struct CPU will have a field global descriptor table. And essentially, global descriptor table in C, it's similar to your homework. It's just an array, right? And essentially, we say for each element of this array, we will do some initialization. We'll use the same kind of macros, and this is just an entry in the array. It says, okay, it's a segment for the kernel code, segment for the kernel data. These two will be initialized with privilege level 0, and segment for user code and a segment for user data be initialized with privilege level user, which is 3 in x86, right? And after that, we say, look, let's load this global descriptor table. Again, very similar to how you do it in homework, saying, okay, this is the address of this array, this data structure, and the size of the array, and this function internally uses this LGDT instruction, which loads it into the hardware register, right? So if you dive a little bit into how those macros are implemented, or how the array is implemented, this is how it works. Essentially, the struct CPU itself, there are some other fields which we will cover later, but for example, there is a current process which is running on this CPU. There is the state of the scheduler. We'll cover those later. So essentially, each physical CPU in a system is represented with this struct CPU structure, right? Since CPU are running in parallel, so those pointers can have different values on physical CPUs, right? And this is how it's declared. It's just an array of this for the n CPU number of available physical CPUs. But what we're worried about it right now is that each physical CPU in x86 will have its own global descriptor table. If I ask you a question, or you should rather ask me a question, why do we need a different global descriptor table on each CPU? And It's kind of impossible to answer right now, but later it will become clear because on each CPU, the kernel will have its own kernel stack. I will explain it in a second. And this kernel stack will be pointed by this task state data structure. That's why each CPU will have its own global descriptor table. So if I kind of like draw you a figure with multiple physical CPUs here, let's imagine we'll have four. We booted with four different CPU. The global descriptor table will have a field which points to the task state. Sorry, up. Started clicking a button on my pen. Oops, that's wrong. That's wrong again. Sorry, I apologize. How do we do this? Like this. So one more time. So if we have a physical CPU, a global descriptor table, GDT, the CPU has a register, global descriptor table register. This register points to the global descriptor table. One entry in the global descriptor table will point to the task state, TS. And this TS internally will point to the kernel stack, K stack, right? And just because this one pointer has to be different on each CPU, another physical CPU will have the same structure. So it will have its own global descriptor table pointed by the global descriptor table register. Internally, it will point to the task state, and the task state will point to the kernel stack. So at a high level, this is kernel stack 1, this is kernel stack 2. The other fields of the global descriptor table will be the same on each CPU, right? So everything else will be the same, just this task states will be different to make sure that on each CPU we have a private kernel stack. It will become clear later, but I just heads up. This is how it works, and we'll come back to it, and I'll explain it a little better when it becomes clear. Then it will become clear. Okay, got it. So in C, each CPU is physical CPU is represented by a data structure. Each CPU has a array of global array of segments represented as a global descriptor table. Internally, this array is just those entries, and you might ask a question how to even encode those entries in C, and you've seen it in a homework. You just use those bit fields. Essentially, you say this is the data structure, segdesk, and you say 16 bits. This specific field represents the low bits of segment limit. The next 16 bits represents the base. The next 8 represent the base from 23 to 16 bits, and so on and so on. So this is essentially how you code it in C. And you saw these guys in the homework, right? So because that's how we define the global descriptor table in homework 3 as well, the same data structure. And again, in a real world, just wanted to stop here. Is this clear? Any questions about it?
So, sorry, I want to go back and ask a question about the CPU struct.
Yeah.
So this is not representing like an actual physical CPU core. This is representing a CPU state.
Correct.
Okay. And so since we can have multiple CPU states with different K stacks, that's why we have the extern array of CPUs, right?
That's one of the, yeah. But also, I mean, that's correct. But also each CPU will have a currently running process, right? Because we will run processes concurrently on each CPU. So this is a pointer to the current process. Each CPU will have a state of the scheduler, because later on we will see that each CPU will run its own scheduler, which will pick a process to run, next process to run from the list of available processes and stuff like that.
So it doesn't even matter that if we didn't have multiple CPU cores. Since we're running things concurrently, we need multiple CPU states like this.
No, if you were running just a single core system instead of this array, one CPU, this array would have lengths of 1 essentially. One CPU would be enough.
Okay, so the number of cores does matter. Okay.
Yeah, because each core, like, I mean, first of all, you started your question absolutely in an absolutely correct way. You said, okay, do we care about the individual kernel stack on each physical CPU? The answer is yes. That's why we have an array of like this is why each CPU has its own global descriptor table, its own task state, and a pointer to the kernel stack. When we will boot into a new CPU, each CPU will allocate a new kernel stack. But along with these three fields, Jesus, music is on, sorry. Along with these three fields, the other fields like the state of the scheduler, the currently running process, the the like the logical flag whether the interrupts are enabled on this CPU, and the nest, like how many times you disable the interrupts and other things like this logical flag, like whether the CPU has started, keep track of each physical CPU in software, right? So essentially, it's like imagine you keep track of inventory in you're building a web store or something, and you keep track of inventory. You're saying, okay, how many items X I have in stock, and this is kind of similar. Or maybe how many, maybe you're tracking the state of multiple stores, right? And you say like in C, I will represent each store as a data structure. So you do the same here with the struct CPU. Does it make sense?
Yes, thank you.
Okay, cool. No, thank you for the question. Yeah, so but again, so there is nothing like extremely super magical here. Like think of yourself as a programmer, developer who says, okay, I wanna keep track of something. And you say, look, I will be using data structures and arrays and everything. And that's what we're doing here. Okay. So any other questions?
Just one question. Do
Yeah.
we care about the consistency between kernel stacks on different CPUs?
And when you say consistency, they are different truly. There's nothing like synchronized between those stacks.
Okay.
We will talk about if you kind of like talk asking about cache coherence and what happens and how multiple CPUs are accessing the same data structures. We will have a lecture on locking and synchronization, and then I will explain how it works.
Oh, okay. Thank you.
But those are typically, I mean, first of all, the question is good, and I wanted to emphasize that, like, typically you never access elements like like the entry 0 on this array in this array will be accessed on CPU 0. Entry number 1 will be accessed from CPU 1. Entry number 2 will be accessed from CPU number 2. And typically all these data structures are accessed exclusively on a single CPU, if I remember correctly. And so, but there will be other data structures like the processes and other things which will be accessed potentially concurrently from multiple CPUs. And we will introduce the ideas of locks and synchronization. And I will again revisit how the cache coherence works, and that it will become clear how everything kind of works together across multiple CPUs. But for now, just like bear with me and trust me that the CPUs will be like concentrate on one CPU. For now, despite the fact that I kind of skipped it and we did detect other CPUs in these functions, and I skipped this function. So this function, like we entered main function on CPU number 0. This function wakes up other CPUs, CPU number 1, 2, and how many you have. And I skipped it for now, so we will come back to it. I just didn't want to like make a detour right now. But just all of it is running on CPU number 0, and just let's think of just one CPU for now. Okay, good. Anything else? Okay, yeah. So essentially, we say, look, we just want to write a global descriptor table and see one interesting observation, which I was kind of pushing forward last time, is that if you carefully look at this code, this one specifically, you might notice an unusual thing. You say, look, you told us about segmentation and you talked about privilege levels. This is privilege level 0. This is privilege level 3. But when you configure the segments, and that was ongoing from the beginning of the boot lecture, all these segments go from 0 to the max address, which is like this all Fs, which is like 4 gigabytes, right? And the user segments also go from 0 to 4 gigabytes, which means that according to this like initialization sequence, the user data segment allow the user, like user code which runs in privilege level 3, this one, access all the memory of the machine from 0 to 4 gigabytes, right? So I keep emphasizing this fact. So segmentation on x86 is not used for protecting the kernel memory, right? I just wanted to make sure that everyone is clear on that, because this is kind of important. There are multiple design choices, right? And you can say, look, by the way, the user segment can only go to the 2 gigabytes and no further. Like essentially you say like the kernel code can access everything from 0 to 4 gigabytes, but the user can only access everything from 0 to 2 gigabytes. And that would be logical, but okay. What x86 and other modern operating systems like Windows, Linux, and FreeBSD do, they essentially say, we're not going to use segmentation for anything for anything but keeping the track of the privilege level. So essentially, all these protection mechanisms are not used. Only the privilege level is tracked. And the logical question now is, but then how do we track, how do we prevent the user code from accessing the kernel? And I mentioned it last time, but I will come back again and I will revisit this. We use the page tables, right? Intel introduced a special bit in a page table. We talked about it, right? So it's, if the segmentation goes from 0 to 4 gigabytes, each page in a page table will have a bit here in both levels of the page table. It's just a single bit. It says either user accessible or not. And if the bit is not set, then the user cannot access the page, right? So the user can issue an address, for example, somewhere over here, like address in a kernel space. However, this page, this yellow page, like essentially because segmentation in x86, the base is 0 and it doesn't shift the address, you will be accessing exactly the same address in a virtual address space. But this page, when it will start translating through the page table, will be one of those yellow pages, which will have this bit set to 0. Meaning that at this point, if the user tries to access the address in the kernel, the segmentation translation passes the check because it's okay, goes up to 4 gigabyte. However, the translation through a page table triggers a violation exception saying, okay, guys, you're trying to access the page which is not user accessible. So sorry, it will be an exception. Exception will be delivered to the kernel, and the kernel most likely will terminate the process with a segfault. So that's what you see on the screen when you see a segfault. Does it make sense? Any questions? Okay, good. So then, okay, page table just has one bit. Essentially, it doesn't allow you to track privilege level 0s, 1, 2, 3. They just said, okay, levels 0 to 0, 1, and 2 can access, and the privilege level 3 is privileged, is special. It needs like this user bit set to 0. So those essentially can access everything. Privilege level 3 can access only the pages which are set with the user accessible bit. And essentially, most operating systems today use just 2 privilege levels, privilege level 0 and privilege level 3 for user, right? 0 for kernel. And it's called a flat segment model. Okay, so we understood it. So this is the bits, the user bits. I will, in my class, I always color code user pages as green, kernel pages as yellow. And like, for example, this is like 2 kernel segments. They are like yellow and orange, and these are 2 greens. So everything user is green. All these physical pages can be accessed by the user. The bits, the user bit is set for the green pages, right? And now, okay, so if we now understand all the privilege levels and everything is cool, right? So we essentially can come back to the interrupt transition. And like kind of come back and figure out how this all works in case when the interrupts essentially are delivered when we're running in privilege level 3, right? So last time, like before the midterm recap, I explained how the transition works when we already run in the privilege level 0, but imagine now we're running in user. Like, so let's take a look at how everything essentially is set up. So for a second, again, assume that we're running with current privilege level 3, or in other words, we're running a user code. This is probably the most appropriate. So we like our instruction pointer is pointing somewhere here, right? So we're executing some user code. And imagine for a second, again, the timer interrupt, which is interrupt number 32, is raised by the hardware. The way it works is that the hardware itself will look up the entry in the interrupt descriptor table. The operating system, and we'll take a look in a second how x86 does it, configures an array in memory, which is called an interrupt descriptor table, which essentially tells the hardware what to do when a specific interrupt is raised. So essentially, if it's an interrupt number 0, the interrupt will look up the entry number 0 in the table. In our case, it's interrupt number 32, so the hardware will go and look up the entry number 32 in this table, right? So, and like the way it works is the CPU itself will have a special register. It will have an interrupt descriptor table register, which the operating system essentially loads. And the interrupt descriptor table itself is obviously in memory, right? So interrupt descriptor table itself will have a pointer to the code segment, which we're switching to. So essentially the two main entries in this, the two main fields in the entry, which we're looking up, entry 32, are the pointer to the handler. So essentially the entry point for the vector 32, essentially the address in memory, which the hardware should start executing instead of this instruction pointer when the interrupt is raised, and the switch of the code segment. So that's why the interrupt descriptor table will have its own code segment in this entry, right? So if we go back here, like each entry in the interrupt descriptor table, it's again 64 bits, and it will have the offset of the handler, which is spread like this in two different fields. But this is essentially, this will point to the vector 32. And vector 32 is just an address. It can be any function. I'm just like x86 uses a human-friendly name, vector 32, hinting that it will be an entry point for the interrupt number 32, but you can call it foobar. Any function will do, right? You just have to be careful about what you do inside this function, because as we see later, you have to carefully save the register state of the user code to make sure that you can restore it later. And this segment selector is essentially a code segment which we're switching to, right? And so the idea is the following. So the hardware will pick up this code segment and switch to it. So essentially, in this entry 32, this code segment will be pointing to the kernel code, because remember, we were running in user code ring 3, and we want to switch into the kernel ring 0. Why is that? Because really this vector 32 or the timer interrupt, the high level goal is to trigger some functionality in the kernel, right? So at a high level, we say, okay, kernel, it's your time to run. But in order to run this code with kernel privileges, we have to switch from ring 3 to ring 0, right? And the switch is encoded by this field of the code segment, right? This field of the code segment essentially says, okay, if the previous code segment was pointing to the user code, this entry in the global descriptor table, so please pick a new entry and switch the privilege. So essentially, this is the way to implement this controlled entry into the kernel. The user can only enter through the vector 32, for example. Like, of course, like it can enter through any of those entries which are configured in the interrupt descriptor table, right? But in this example, it's vector 32. And it allows the the operating system to allow the user to switch from ring 3 to ring 0, right? Does it make sense? Any questions? Okay, so obviously one question which we have right now is whether we can continue on the same stack. Remember, when we didn't do the privilege the privilege level change, the hardware was just pushing the state of the currently running process on the stack, right? Because like essentially, since you're switching to a new instruction pointer, you have to push the old instruction pointer on the stack here, right? So this instruction pointer, which we were executing right before the interrupt, right? And in other fields, right? But here, the question is that, is it safe to allow the hardware to save something on the current stack? So because the currently instruction, like the stack pointer, ESP, points to this location, right? Which is in user memory, somewhere over here. The question, is it safe? What do you think? We discussed it many times in class, right? And so the obvious answer is what? Anyone? Everyone is quiet. So no, it's not safe because the user can make sure that can set this is stack pointer to point anywhere. It can, for example, point to somewhere in a kernel memory. And obviously, if the hardware will save something here, it will override the kernel data structures. For example, one obvious candidate is to put the instruction, put the stack pointer pointing to the, leave the stack pointer to point in the interrupt descriptor table, or for example, somewhere in a page table, which will provide the user with the way to override the page table, right? And since, after that, you may craft carefully values of the registers which the hardware saves, and so it essentially will override whatever you want in a kernel, right? So it's not safe. Like the kernel itself cannot trust the value of the instruction, the value of the stack pointer in the user program. It can point anywhere. It can point to a page which is not mapped, and it can trigger an exception, for example. Okay, for this reason, every time, in order to like implement this controlled entry into the kernel stack, the operating system will configure a dedicated kernel stack. That's the one which I was discussing earlier in the lecture in this diagram. So this is the kernel stack. Every time, sorry, where is it? Up here. Nope, not here. We scroll back and forth. So this stack. So essentially, every time you start a process, instead of just having one stack in user level, each process will have two stacks. One in user level, this one, and one in the kernel. So essentially this one. And this kernel stack will only be used when the process performs a system call, as we will see later, or is pushed into the kernel through an interrupt transition. For example, like this one, vector 32, like a timer interrupt. The question is like how the hardware can locate this new stack. And okay, we can like come up with different ways. The way Intel does it, the Intel introduces this task state segment. So essentially, remember in my drawing just a second ago, this task state segment is a segment which points to the kernel stack. It allows you to track the kernel stack. So this is the pointer here. And the entry in the global descriptor table points to the task state segment in memory, right? So this is the data structures which I was drawing here. Let me just quickly context switch here. Make sure that we have it. Just I was hoping I can switch quickly to this. Just disable it. right? Essentially, like the data structure which I was drawing here in this diagram, global descriptor table points to the task state, which is here, points to the kernel stack. Those are the three which we have right now here on this slide. Essentially, when you enter into the kernel, the hardware says, okay, I will locate the new code segment by figuring out an entry in a global descriptor table. I will figure out a new stack by using the task state segment, which is yet another register here on the CPU, which is points to the entry in the global descriptor table. This entry points to the task state data structure. This task state has a tons of fields which were historically this pointer. And after that, the hardware says, okay, I have the kernel stack. I trust it because the user cannot change the fields of the task state segments, cannot change the global descriptor table. So the hardware essentially pushes the state, the current state of the process on this new kernel stack. So essentially, like what I wanted to show here is those yellow fields, which I don't have them here. So essentially, these 5 fields will get pushed on this kernel stack. Those 5 fields are immediately changed in this transition, because if you remember correctly, in the first when the interrupt happens without changing the privilege level, only these 3 fields are changing. The E flags register can change because it contains the interrupt flag, which keeps track of whether interrupts are enabled or disabled. The code segment will change because the entry here can pick a different code segment, and the instruction pointer changes because you're essentially jumping to the new address in the memory to execute the instruction, to execute the interrupt handler. When you transition between privilege levels, these 2 additional fields can change as well, because you're picking a new stack and you're picking a new stack segment. So now hardware, instead of saving just 3 fields and potentially sometimes pushing an error code here, it pushes 2 additional fields, which are related to the stack. Stack pointer ESP, the old stack pointer, which was pointing here, and the stack segment, which was the old, essentially, the stack segment of the old of the user code stack segment. These 2, right? Make sense? Okay, let's walk over it again. So what happens here is the following.
Excuse me.
Yeah, go ahead.
I have a question. So,
Yeah.
if we were saving the user state before we changed our permissions, would we still need the TSS and the separate kernel stack? Because then, like,
Wait, hold on. Say this again. Like maybe
So-
rephrase what we said before we were changing what?
so in the diagram we just showed, we switched to kernel permissions and our new stack, and then we added the user state. If we added the user state while we were still in the user mode, wouldn't that prevent any like malicious actors? Because if they modified the stack pointer, it would be a segmentation fault when we were moving theirs, when we were adding their state before jumping to the kernel.
Still cannot parse the question real. Like maybe can you rephrase? So currently, okay, we can do a couple of things here. We can go back. Okay, let's go back. How can we do it? Let's quickly go back to the case when the interrupt transition does not trigger a privilege level change. Let's just first take a look at it. We did it before the break. So before the break, if you're running in already, imagine for this second, you're already running in a kernel. You're running in ring 0, right? You trust the code. You trust the code that it will not reset the ESP pointer to point to some bogus memory which can overwrite whatever in a kernel, right? You just say, well, because I wrote the kernel, I trust it, right? So I trust that ESP points to some valid kernel memory, which means that the hardware can simply push these additional values on the stack here, right? like essentially continue pushing on the stack, and specifically we'll push 3 values here, right? And the hardware will just go into the interrupt descriptor table, which is pointed by this hardware register, which the kernel initializes. Since it's interrupt number 32, it will pick the entry number 32 in this table, in the interrupt descriptor table. The 2 fields which we care about is the address of the handler, essentially the entry, the address of the function which starts processing the interrupt, and the code segment. What we don't really change the code segment, we stay with the same code segment, right? So we don't emphasize it, right? And essentially what I was saying, there's 3 fields here where the E
Fuck
flags.
you, Max. Asshole, bitch. Just kidding.
Can you maybe mute before yelling? E flags, code segment, and instruction pointer, right? So these 3 are pushed on the stack, and some additional interrupts, they push error codes on the stack, right? And because those fields can change immediately, and unless the hardware changes them, you will never be able to come back and return from the interrupt to essentially start executing the code which is here under the instruction pointer, which you were executing before the interrupt timer comes, right? Make sense? Now, today we say, look, but what if we're not running in ring 0, but instead we're running in ring 3, right? Which means that, okay, guys, so we are running in user, we have to transition back into the kernel. So a couple of things are important. First of all, we need a way to switch from 3 to 0, and we also need to make sure that there is no possibility for the attack, meaning that whatever the user is doing, whatever the registers are, user can set instruction pointer to some weird place in the kernel. User can set the stack pointer to some weird place in the memory. It cannot overwrite memory of the kernel or read memory of the kernel. And the hardware comes up with this new interface. They say, okay, guys, we understand that you don't trust the user level, so the user value can have the user code can have any values for instruction pointers, stack pointer, stuff like that. And instead, it came up with this idea that first, let me erase everything on this slide. Since we don't trust the value of the stack, we can't even save those 5 values here anymore, or 3 values anymore, because maybe this memory is not mapped, and the very first attempt to save something here will trigger a page fault or potentially overwrite kernel memory, right? And the user can set the ESP value to any value at once, right? Because when we compile the C program, or we can link against an assembly file, and this assembly file can have something like move ESP equals 0, for example, to just set, or ESP equals FFF or something, right? So any value in memory. So for that, the hardware says, okay, we'll allow you to configure as trusted, protected stack in a kernel, right? And instead of saving anything on this user stack, the hardware will save the state of the running program on this new kernel stack. And after that, everything is relatively simple. So essentially, the question is how to find this stack. The hardware says, okay, look, we'll introduce another data structure, which is called task state segment. This will have a pointer to the kernel stack. The next question, how do you find this task state segment? I think TSS. Okay, let's call it TSS, task state segment. This will be found by looking up the value in the global descriptor table. I mean, it's a little bit weird, right? Instead of having a direct pointer to the TSS somewhere in hardware, they said, okay, well, that's right. And instead, we will have a pointer to the global descriptor table, and it's a full descriptor, right? Same kind of layout as every other descriptor, but the base of this descriptor will be a pointer to the TSS. And inside the TSS, there will be a pointer to a kernel stack, right? So that's how it works. And now, okay, back to your question. So what are you trying to ask? So you're trying to suggest a different protection scheme which achieves the same goal, or you want to clarify this scheme?
Yeah, that kind of answered my question. Yeah.
Okay, good. Any other questions? So everyone is good? Everyone understand this interrupt transition now? So let me go back and just reiterate these 5 fields which are essentially saved. So what happens here is the following. So we have, if in the past only 3 fields can change, right, could change. It's instruction pointer, code segment, and the E flags registers. And these 3 fields, like it's the state of the CPU, essentially, this part of the CPU. Now we have 2 additional fields because the stack segment and the stack pointer itself can be changed as well. So the hardware changes 5 fields. So more specifically, the processing of the interrupt goes like this. It says, okay, we will save the values of the ESP and the stack segment in an internal CPU register for a second. We will load these values, the new values of a stack segment and the ESP from the TSS table, right? After that, we will push. So now, because now we have the value of the stack, because that's why we don't have this, we don't have the stack here in the step 1. That's why we're saving them into the some internal register for a second. Now we have those values because we have a stack. So now we push these 5 things: stack segment, stack pointer, user flags register, user code segment, and user instruction pointer onto this new stack, right? So this stack is pointed by this register, by the stack pointer, right? And after that, we say, okay, we're ready to run the new the new interrupt handler. So the vector 32, we pick the instruction pointer for this handler and the code segment, and this code segment will have the privilege level equals to 0, right? From the interrupt descriptor table at the offset, which is pointed, like essentially it's entry number 32, right? Because we're processing interrupt number 32. After that, we say there is an additional trick here. I will explain it a little later. So the interrupt transition can either disable further interrupts or leave them open. So essentially, a system call does not disable the interrupts. It just works more like a function. So it just says, okay, I will go into the kernel, but further interrupts are still enabled. And this is the idea here. So if we go through an interrupt gate, we will clear the further interrupts. But if not, then we don't. We'll talk a little bit about it later. So don't worry about it right now. And essentially, at this point, you say, well, I can start executing the handler, essentially the function which is pointed by this instruction pointer, which we've found in the interrupt descriptor table. And in our example, it's vector number 32. Make sense? Okay, let's quickly do a poll, since we are doing a lecture. So let me enable this question on poll everywhere. So you have to tell me which fields are saved on the interrupt transition when you change the privilege levels. Someone is not muted. I'll mute some people. Just sorry, apologize. Just to make sure that everyone else is just. Well, grab my charger to make sure that I'm not running out of battery. Okay, everyone answered? I see that the answers are still changing. Man, probably. But everyone on Zoom, does anyone on Zoom need more time? Let me close the poll for a sec to enforce fairness for the people who are. Okay, so we got the point. So the 5 fields are saved. So essentially stack pointer, stack segment, instruction pointer, instruction segment, and the E flags register because the interrupt transition can either disable the further interrupts or keep them on, right? Make sense? Okay, so if we understand how interrupts work, let's take a look at essentially what happens in the interrupt descriptor table. This is just one more time before we go. It's essentially this is how the transition looks. If this was a user stack and we're changing the privilege level, nothing gets saved on the user stack. Instead, we save those fields in this order on the kernel stack. So essentially stack segment, instruction, stack pointer, E flags, code segment, instruction pointer, and the error code in case the interrupt pushes the error code. Some interrupts do. And just to remind you, if we didn't like trigger a privilege change, everything was changed, everything was saved on the same stacks, essentially. If your stack pointer was pointing to some value, foobar here, before the interrupt, these 3 registers get saved and some occasional interrupt push the error code. Everything stays on the same stack. Okay, if you ever want to, again, think about the full interrupt transition, that's the slide which kind of captures it in case of a privilege change, right? So like this is the kernel stack, this is the 5 things which get saved on the kernel stack. And like if you carefully look at this data structure, you will remember what triggers what. So essentially, this is the entry point into the interrupt descriptor table, points back to the GDT. A TSS is located like this. Like I should probably add this 2 lines as well. TSS picks the stack, hardware saves everything on the stack. Okay, what I wanted to do next is to essentially discuss the content of the interrupt descriptor table. So essentially this. So interrupt descriptor table, the layout of the interrupt descriptor table is specified by the Intel CPU itself. So essentially the CPU says, okay, look, first of all, the first 32 entries will be reserved by Intel itself, meaning that Intel says, okay, a specific number will be used for a specific purpose. So for example, this number 14 is a page fault, essentially. If you're trying to access a memory address, which triggers the page walk. So essentially you say, look, I will be walking the page table and at some point I will hit the page table flag, which is not present. At this point, I am like, okay, that triggers a page fault. And I mean, like, I bet that all of you, like, even before this lecture, you heard the words page fault, but now you essentially know how it works. So the page fault itself is just the reaction to like an error in the page walk pass, right? And other interrupts reserved by Intel serve similar purposes. So for example, some language compilers which try to trigger an undefined behavior, they use this specific instruction, which is undefined opcode, and it will result in the exception number 6. For example, if you insert a software breakpoint, it uses an int3 instruction, like it's the XCC. If you look at the instruction opcode, it will be XCC. So this one triggers breakpoint, so exception number 3. If you're dividing by 0, you are resulting in exception number 0. So it's a debug error. And so essentially, I don't want to go through all the interrupts because they are probably not as important right now. So the ones which are important are the page fault. If you're, for example, doing your homework and you suddenly hitting a page which is not mapped, the QMU will like tell you, okay, the hardware essentially first encountered a page fault. Most likely, since you don't have support for page faults. Let me just guys, let me mute you real quick.
是不是重启和什么蓝牙关了再开一下那种感觉？
How do we do this?
嗯，
Supposedly should have permissions to mute people. Okay, done. Thank you. So essentially it can trigger a page fault since you don't, in your homework, for example, you don't have support for a page fault. Most likely the hardware then says, okay, it's a double fault. So essentially a second fault will be delivered as exception number 8. Since you don't have support for a double fault, it's a triple fault, and at this point the hardware just reboots. So that's probably what you've seen where you were booting QEMU in this last homework, and essentially if you misconfigure the page table, that's what you're gonna see, right? Make sense? Okay, so that's the layout of the exception table, interrupt descriptor table. The first 32 exceptions are reserved, but the other ones, like above the 32 and up, the max number on Intel is 255 because the table is limited to 256 entries, are user configured interrupts. And those other interrupts are actually interrupts from device drivers or from a timer. So for example, the timer was using the first available unreserved interrupt, which was interrupt number 32, right? It's just a convention, so you can, technically speaking, probably enable timer on a different interrupt. But on Intel machines, typically the first 16 interrupts, like above the 32, are reserved for legacy devices, and those are called IR2s. That's just another name for it, right? And a timer, one of them. But don't get surprised that the first 32 are reserved by Intel. The first available is 32, and this one is used by the hardware, so it's reserved by the platform. It's an interrupt delivered from the timer, right? That's why in our example, it was an interrupt number 32. Make sense? Any questions about the table? Question on chat. Can you reopen the poll? We'll figure it out later. We should understand a couple of things about the interrupts, right? So interrupts can be synchronous, kind of like if you divide by 0. So it's in line synchronously in the program. And those interrupts cannot be disabled because it doesn't make sense to disable a division by 0, right? So even if you say, I don't want to process division by 0, but there is no real logical way to move forward. And so the synchronous interrupts cannot be disabled, right? But the interrupts from the hardware devices, which are like from 32 to 255, those can be, the Intel uses the word masked, but in other words, they can be disabled. And the 1-bit interrupt flag in the eFlags register controls whether those interrupts are masked or unmasked, right? So essentially, like you can, like the very first instruction when we started booting in the boot code, the very first instruction which we executed was CLI. The CLI instruction essentially cleared the interrupt flag bit, setting it to 0 in the eFlags register, essentially disabling all the interrupts from external devices, right? If in the next instruction we do a move which accesses the memory which is unmapped, we trigger a page fault. And of course, this page fault will not be disabled because it's a synchronous interrupt, because this instruction triggers it, right? So synchronous interrupts cannot be disabled, essentially, right? So it just doesn't make sense. But all external interrupts are disabled by essentially clearing the flag in the eFlags register, right? And so if we did this CLI for until we reset the, like, set this flag back to 1, the timer interrupts will not be delivered to the CPU, right? Make sense? There is one exception. However, Intel allows one privileged interrupt, which is called unmaskable interrupt. It's delivered through vector number 2. So it's interrupt number 2 in the interrupt descriptor table. And this non-maskable interrupt does not obey this interrupt flag. So essentially it will be, it's an interrupt, it's an external interrupt, it's asynchronous, It's delivered from an external device, but it's still unmaskable. This interrupt, if you can guess, it's reserved for some critical events. For example, you're accessing a memory and the hardware says, okay, guys, I believe that the memory is like there is a bit flip and the memory read fails, or something is going on the chipset. I don't know, maybe we're losing power. And so this is kind of the last chance for the system to react in some manner to this critical event. So, and this non-maskable interrupt will not follow the rules of disabling the interrupts with the interrupt flag. However, only one non-maskable interrupt will be delivered. The second one will not be delivered. It will wait for until you process the first one, right? So those are the rules. It's a little like, I agree, it's a little unusual, and but still yet, that's how it works. Does it make sense? I like this non-maskable interrupt is entry number 2 in the interrupt descriptor table.
Aren't
Okay.
there many non-maskable interrupts? Oh, never mind.
No, you're right. So it's actually true. The way it works is that multiple hardware things can trigger a non-maskable interrupt, and an operating system can configure which ones become non-maskable. So essentially, when you program the interrupt controller, you can say that, please, in case of this event, instead of like using some interrupt number which is above this 32, for example, interrupt number, I don't know, 64 or something, deliver this interrupt through the vector number 2, and then it becomes non-maskable. So for example, another example of a non-maskable interrupt is if you know how the statistical profilers like OProfile or perf work, they essentially use hardware counters to count the number of executed instructions. And you say, every 10,000 instructions, please send me an interrupt, and I will try to detect which instruction was executing, and I will try to reconstruct the performance profile of the program. So typically those are configured as non-maskable, because if interrupts are disabled for a long time, then you lose this information, and you typically want to process them as fast as possible. So, but you're right that multiple hardware events can be delivered as a non-maskable interrupt. And then you have to distinguish by looking at the hardware flags which specific event actually raised the non-maskable interrupt. In x86, we're not going to see the non-maskable interrupt. x86 doesn't support them, but essentially x86 will be reacting to this first, like essentially from 20 to 23, like as of like 5 years ago, those were not used by Intel, by this x86 initializes up to 19, I think, and the hardware interrupts from 32 plus 16. That's the stuff we're going to see in x86. Make sense? Okay, so non-maskable interrupts. Let's now take a look at the x86 source code. Essentially, how does x86 initialize the interrupt descriptor table to make sure that everything runs, right? And again, we're back to the main function. So everything happens still in main. And now, like if we earlier looked at this one, Jesus, what does it cancel? We looked at how the secinit initializes the global descriptor table. This one, trap vector initialization, trap vectors, initializes the interrupt descriptor table. Traps are yet another jargon for interrupts, for specific flavor of interrupts, so it doesn't matter that much. So essentially, if we go inside this TV init function, x86 uses a loop, which is not surprising, from 0 to 255. And it says, okay, I have an array in memory which represents the interrupt descriptor table. And for each entry of this array, I will essentially assign a specific vector. So it has a collection of vectors. So those are function pointers. Like, for example, vector 32. And I will essentially initialize this table. And I will make sure that all of these are initialized with a kernel code privilege, meaning that they will trigger a transition into the kernel, right? Even if you were using it with privilege level 3, the code segment. So essentially this field sets a code segment in the global descriptor table, and this field sets the offset of the handler, right? Okay, so a couple of interesting things here. xv6 also will use an interrupt, and this is the number tsyscall. It's a number, I think, 64. And this specific interrupt will also be initialized with privilege level. The only distinction here is that this fields, all of the entries in the interrupt descriptor table will use this value as 0, and this one is 3. And the idea here is that if user suddenly has an int 6 instruction in the code stream, or like, let's say, int 14, right? This, technically speaking, like, imagine like you use assembly code, int is a valid instruction. You say, look, I will try to invoke a page fault, right, in your program. Well, it's allowed technically, right? Because this int instruction, it will be executed by the CPU, will go through the interrupt descriptor table, and will trigger, like, essentially trigger a page fault interrupt. However, this is kind of insecure because it will confuse your system, because in practice, it's not a real hardware page fault. It's just the user tries to invoke the int 14 instruction. And that's why essentially by setting this field to 0, we control that only at privilege level 0, this interrupt transition is allowed, right? Meaning that like if user tries to invoke this interrupt, the hardware says, instead of delivering exception 14, it will deliver exception protection violation, which I think is 13 or something like that, right? And but for the syscalls, in order to enable the syscall, essentially user will be able to invoke int 64, and for this specific interrupts, like to be to let the user invoke it with privilege level 3, right? User runs at privilege level 3 and essentially trigger a correct transition through the interrupt descriptor table. This descriptor privilege level is set to 3. So it's a protection mechanism, right? So essentially, like, as I was saying, user cannot invoke any of the interrupts, for example, a page fault, and this protection violation and exception, stuff like that, right? But we allow the user to invoke the interrupt number 64. And the rules of this is the following. So if this is an entry in the interrupt descriptor table, this entry will have a descriptor privilege level. And the rules of the CPU is the following, are the following. If the current privilege level is less or equal, meaning if it's 0, for example, less, more privilege, or equal, for example, another 0, to a descriptor privilege level, this field, then the user can invoke or trigger this transition. If, however, it's not equal, so if the current privilege level is 3 and this descriptor privilege level is 0, the user will not be essentially trigger and transition through this interrupt gate, right? So, for example, the user will not be able to invoke interrupt 32, kind of like saying, okay, it's a timer interrupt, right? Because this descriptor privilege level will be set to 0 according to this code. Essentially, this loop sets all the entries which privilege level 0 here, and only one with descriptor privilege level of a user of 3 here, making sure that only the syscall is the only interrupt which the user can invoke. Does it make sense? Did you understand this protection story? So it's a little unusual because, like, the CPUs are designed to make sure that ring 3 cannot harm the kernel, and everything is designed in such a way that you carefully configure those fields to make sure that the user cannot violate this protection boundary. Any questions? So this is essential. This is what I wanted to emphasize. Everything is 0, only one is 3. Another thing which I want to emphasize is the following. All the interrupts are configured with 0, and only the system call sets 1 here. So the meaning of this 0 and this 1 is the following. Like I mentioned the word trap before. The trap is a system call. The trap is an interrupt transition which does not enable further interrupts. I will not be using this term often because I don't remember it myself. It's like back in the days, interrupts were used for many different things, and one of them was like this trap. And so people used to distinguish them. Right now, the only interesting detail which you have to remember that this flag essentially, the 0 or 1, tells the hardware. Remember that I said that when you transition through the interrupts, you can change the E flags register. And specifically, the only bit in the E flags register, the interrupt flag. This interrupt flag can be reset to 0. So essentially, maybe interrupt flag was 1, and if you essentially, if this field is set to 0, then when you go through an interrupt, 1 is changed to 0, meaning that the further interrupts are automatically disabled. However, in case of a syscall, the x86 makes a choice not to disable further interrupts. So for example, in case of a syscall, if this interrupt flag was set to 1, the user performs a syscall, it will not be reset to 0. It will stay 1, which means that we go through the interrupts, but the E flags register doesn't change, and essentially, like, further interrupts are still enabled during the system call. Does it make sense? It makes sense because the system call is more like a function call in a kernel. So if you do something like sys read triggering a file read in a kernel, it's more like you calling a function in a kernel, except that you cannot call a function read directly in a kernel, but instead inside the read, as we will see next time, there will be an int instruction, int tsyscall, which essentially says, okay, I will trigger a transition through the interrupt description table. Inside the interrupt descriptor table, there will be a pointer to vector 32. Oh, sorry, not vector 32, vector tsyscall, which is number, I think, 64. And then eventually this code pass will lead you to the system call sysread. But since it's more like conceptual, it's more like a function call, it doesn't make sense to disable further interrupts. Does it make sense? Okay, so let me stop here and let me essentially, we're done looking at the interrupts, the basics of the interrupt mechanism. On Thursday, I will come back and I will explain how the interrupt pass is implemented through the x86 kernel and how the interrupts are used to implement system calls. So essentially, if we kind of have bits and pieces of what the interrupts should do, now we will take a look at how specific code which implements the interrupts in the Linux, in the x86 kernel. And then on Thursday, we also will assign you a homework which will ask you to extend x86 with yet another system call, right? Any questions right now? All good? Okay, I'll see you then on Thursday. Thank you.
Thank you.
Okay. Here's the question. If you're going to cut